Hello students, in this video we are going to discuss about Young's double slit experiment, and we're going to solve numerical problems based on this topic which were asked in HS final examination, some higher secondary education council. Okay, and before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT 123. That's my Insta ID. You can follow me on Insta. So now let's start. Now you see, suppose we have a plan here and we have two slits on this plan, means two very fine holes, okay, S1 and S2, right? And this is one screen, okay. And now you see, and light is allowed to fall on this plane, okay. Then the light will pass through these two holes, S1 and S2, and it will spread this way, okay, from both S1 and S2, right? It will spread this way in all directions, like this way. And here you see, that's how it will continue to this screen, okay. And on the screen we're gonna get bright fringe, dark fringe, so on, bright, dark, bright. That's how we're gonna get, okay. And now you see, when two waves, this is one wave and there is another wave, suppose if they superpose at some point, if they overlap like this, okay, either trough on trough or crest on crest, okay. If two waves overlaps like this, here they suppose superpose, okay, then we're gonna get constructive interference. And here we're gonna get at this point, if they superpose like this, then here we're gonna see the bright fringe, if this is the screen. If suppose when two waves during superposition at a particular point, if crest of one wave comes over the trough of another wave, then here we're gonna get destructive interference. That means here we're gonna get dark fringe, okay. So hope you have understood this. Now suppose here you see, let me clean this first, okay. So here we have a source S, this is one source, and light is traveling from this source, and these two small holes will act as two coherent sources. Coherent sources means two sources of waves, okay. That means here you see two sources of wave with constant phase difference. That means phase difference between their corresponding points will be constant. Here you see, okay, phase difference at these 2 points same as phase difference at these 2 points, same as phase difference at these 2 points, right? Hope you have understood this. So then these two sources will be called coherent sources, right? So hope you have understood. So now let me write what I have explained now. So now as you can see, when these waves of lights are propagating from these two sources, like you can see the point of intersection, these points of intersections, right? So such points will appear on this screen as well, okay. At those points, if we have crest on crest or trough on trough, then here at that point we're gonna get bright fringe, okay. If we get trough on crest like this, okay, then we will get dark fringe, okay. Hope you have understood this. So now you see, first let me clean these things, okay, sorry. So here you see, just give me a second, okay. Now you see, suppose this point here O, this is the point O, which is equidistant from these 2 points. Suppose these are two lines from these two sources perpendicular on the screen. This is suppose A, this is suppose B, and O is the point between them. Okay, if the distance between the two slits is small d, then this is d by 2, this is d by 2. Okay, this is d by 2 and this is also d by 2, right? So now you see the light waves traveling from these two sources, S1 and S2, when they will reach the point O, okay, at this point, okay, which are equidistant from these two sources, as this point O is equidistant from these sources, that means S1O equal to S2O, and at this point, and you see these two waves actually originated from the same source of light, as these two poles act as coherent sources. That's why we are getting two sources, but originating from the same sources, emitted from the same sources actually. So that's why at this point, okay, so where here we're gonna get constructive interference. Okay, so that means we're gonna get the bright fringe, and this is the position of central bright. Okay, as this 2 point as this O is equidistant from S1 and S2. Then next we're gonna get dark, then again bright and dark, like this on both ways, up and down. Okay, so now you see, suppose we have a point P on the screen like this. Suppose, give me a second, suppose we have a point P here, this is point P, and this point is at a distance x from O. Okay, suppose these two waves, they must have a path difference. Here you can see, if we draw a perpendicular here, then this distance is the difference between these two waves. S2P minus S1P will be equal to this portion, right? Let it be del y, let it be del y. Okay, so this is the path difference between these two waves. Okay, so but the light waves traveling to the point O, these two waves that meet at O, they have zero path difference. Okay, here S1O is equal to S2O, right? So hope you have understood this. So let me consider this distance is small d, this distance is suppose capital D. Okay, and P is at a distance of x from the O. Okay, so now let me draw the diagram properly and let me write what I have considered here. Okay, so give me a few seconds. So let me complete this first, let me make it faster. Okay, so P be the point on the screen at the distance x from O, path difference will be as this. Okay, so that's all I have written, what I have explained till now. So now you see, let's find this path difference. Okay, how to find it? Let me go to a new slide, let me take a new slide. First let me copy this diagram. I need this diagram to explain these things. Okay, let me copy, let me take a new slide here. So let me paste the diagram here. This is the diagram. Now in order to find the path difference dy, that is equal to S2P minus S1P, so first let us take the triangle S2PB, this triangle S2BP, this triangle. Hope you can see this on the figure. Okay, S2PB, this triangle, right? So from triangle from triangle S to BP. So if you apply the Pythagoras theorem here you can see this is the hypotenuse and here is the perpendicular, PB is the perpendicular and S to B is the base. Okay, then S to P square must be equal to PB square plus S to B square. Okay, now PB, this length PB, this one here you can see this PB, this is PB, so this is equal to x plus d by 2. This portion is d by 2, right, plus x. Okay, so here we can write, instead of d by 2 we can write x plus d by 2. So PB square, so x plus d by 2 whole square. Now this SB is nothing but d, right, this is d square here. Okay, so now you see if we simplify this, how to simplify this, let me take d square common. On taking d square common, what we will have, we're going to have x plus d by 2 whole square divided by d square plus 1. That's what we're going to have, right? Now it can be written this way also, 1 plus x plus d by 2 whole square by d square, right? If you multiply this d square with 1, then you're going to get d square, and if you multiply this d square with this, then d square will be cancelled and you're going to get this term, right? Hope you have understood this. Now let me take square root on both sides in order to get S to P. On taking square root, this d square going to be equal to d, and the term within the bracket, let me write this, d square. So here we're gonna get power half on taking square root, right? So hope you have understood this. Now let me expand this part using binomial theorem. I hope you know this expansion. If you don't know, just remember for the time being, 1 plus x whole to the power n is equal to 1 plus n into x plus n into n minus 1 into x square by factorial 2. Factorial 2 means 2 into 1. Factorial 3 means 3 into 2 into 1. Factorial 4 means 4 into 3 into 2 into 1. Hope you know these things, right? Then plus n into, next term going to be equal to n into n minus 1 into n minus 2 into x to the power 3 divided by factorial 3 and so on, right? Okay, hope you have understood this. And for this expression here, value of n is half. Okay, and we're going to consider this term as x. We're going to consider this as x, and using this expansion, if we expand this part, then what we're going to get, S to P is equal to d into, so first term is 1, okay, next term is n into x, next term is n into x, this is n into x, so here n is half, okay, n is half, so let me write half, and this part is x, this part is x, okay, this part is x, so let me copy this, so this is x, right? Then plus next term going to be equal to n into n minus 1, that means half into half minus 1, okay, into x to the power 2. X to the power 2 means we have to take this term, and here we have to take square and divided by factorial 2 plus dot 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 so on, right? But here you see these terms with higher power on this, okay, so here we have taken this term, and here power on this term is 1, and here it is 2, and next term, in the next term the power on this term will be 3. and we're gonna neglect this power on this term, higher powers on this term, this x plus d by 2 by d square. Okay, we're gonna ignore this term, and next term, the where we're gonna get cube, where we're gonna get 4. Okay, all those terms will be neglected, because you see this pb is less than this distance d. Okay, so here d is greater than x plus d by 2. Okay, therefore if you divide x plus d by 2 by d, then you must get a number less than 1. Suppose, let me take an example of a number which is less than 1. Suppose 0.1. Okay, now this is 0.1. Power on 0.1 gonna give you 0.1. 0.1 to the power 1, that's gonna be 0.1. Now if you raise the power, if you take power 2 on it, then it's gonna give you 0.01. now you see, higher the power on this smaller numbers become, so here you see, compare the power, higher the power, smaller value, right? Hope you have understood this. So that's why for higher powers we are getting smaller values. That's why we're gonna neglect these terms with higher powers on this, right? Hope you have understood. So we're gonna take only first two terms. Okay, so it can be written this way also. Instead of writing half, here we can write 2. Okay, so hope you have understood this. So now you see, let me copy this here. Okay, this is what we have got, right? So here we're gonna write using binomial theorem, using binomial expansion, and neglecting the higher powers. Okay, of the term x plus d by 2 divided by d square. Okay, so hope you have understood this. So this is what we have got. This is S2P, right? This is S2P. Now let me find S1P. This S1P. Okay, S1P. Okay, now let me clean these things. Just give me a second. Okay. Now, okay, let me clean this part also. Now you see, from this triangle, this S1PA, from this triangle. Okay, so here you see this PA is equal to x minus d by 2. Okay, this part is x, this part is x, and this part is d by 2. So this part must be x minus d by 2. Hope you have understood this, right? So as this part is x, okay, and this part is d by 2, so this portion PA, that's going to be equal to x minus d by 2, right? So hope you have understood this. So now this part PA, this is x minus d by 2. Okay, now this is nothing but d. Okay, so again, as we have done, as we have obtained SP as S2P, similarly from triangle S1PA, so we don't need to show all the steps. If you write similarly, then it will be fine, because the process will be same. That's why I'm not gonna repeat all the steps. Okay, similarly from this triangle, this time from this triangle, if you apply the Pythagoras theorem, then if you expand using binomial theorems and neglect the higher powers, then you will get S1P is equal to, instead of x plus d by 2, here we're gonna get minus this time, because this distance, this PA is x minus d by 2, right? So that's why S1Pu will be is equal to d into 1 plus x minus d by 2 whole square divided by d square, 2d square, not only d square, sorry, 2d square, bracket close. Right, let me write it properly. So this is what we're gonna get. Right, hope you have understood this. Let me write here, just give me a second. Okay, so this is what we gonna have. Just hang on. Okay, so this is S1P. So now we have got S1P and S2P. Now we can find the path difference, this S2P minus S1P, right? So now let's find that. Okay, first let me copy these two expression and let me take a new slide. Okay, this is S2P, so here it is S2P. Now S1P, this is S1P. Okay, this is S1P. So now path difference del y, which is equal to S2P minus S1P. Let me draw the diagram as well. Just give me a second. Let me. Okay. So here is the diagram. You see, this is the diagram. Okay. So now let me replace this S2P by this result. So then del y can be equal to, sorry, this is S2P and this is S1P, right, minus. So now let me solve this. How to do that? Okay, let's take d common, right? Then within bracket we're gonna have 1 plus x plus d by 2 whole square divided by 2d square, then minus, and on opening this bracket here minus 1 minus x minus d by 2 whole square, then 2d square. That's what we're gonna have. Okay, so here minus 1 plus 1 gone, and d into here 2d square will be, you know, LCM, and here we're gonna have x plus d by 2 whole square minus x minus d by 2 whole square. That's what we're gonna have. So d square cancels d, right? So here we're gonna get 2d only, and you see we know that a plus b whole square minus a minus b whole square, that's gonna give you 4ab, right? Hope you know these things. So if we apply this here, then what we're gonna have here, we're gonna have 4x d by 2 by 2d, right? So here 2 cancels this, and this 2 cancels this 2. So here x d by capital D, that's what we have got, right? So here is the path difference that we have got. Now let me go to a new slide. Okay, so what is the path difference we have got? Del y is equal to x small d by capital D, and let me draw the diagram as well. First let me copy this diagram. Okay, now here is the diagram. You see, this is S1. Now you see, suppose if these two are the sources of two waves, okay, here you see, if they overlap like this, okay, crest on crest, okay, then here we should get you know, here we will get bright interference, and in that case the path difference between these two waves, that must be equal to integral multiple of lambda, either 1 lambda, 2 lambda or 3 lambda. Okay, so if the path difference is like half lambda, 3 by 2 lambda, so on, in that case then crest of one wave will be on trough of another wave. In that case we're gonna get dark fringe. Okay, hope you understood this. So now what is the condition for you know, bright fringe? You know, condition for bright fringe. Okay, so that path difference del y, that must be equal to integral multiple of lambda. so n may be equal to 0 plus minus 1. Let me write just 1. Okay, 0 1 2 dot dot dot, so on, right? So now you see here, actually we can write plus minus here. You see, I will tell you the reason. First let me do something. So we can replace this y by this. Okay, then what we can write, so x d del y is nothing but x small d by capital D and lambda. So in that case x will be equal to n lambda capital D by small d. That's what we have got. So it gives the position of nth bright fringe. Okay, so it gives position of nth bright fringe. So this is the position of nth bright fringe. Now you see, actually the value of n can be positive 1, negative 1, positive 2, negative 2, because you see, so here you see this is the O, this point is O. If this position, if the nth fringe is here, if this is the position, okay, here, if it is plus x, then at the same distance below this O we can consider minus x, right? So hope you have understood this. That's why we can write here value of n is equal to either 0 plus 1 or minus 1 plus 2 or minus 2. Okay, we can consider that plus minus 2, right? So this is the position of nth bright fringe. Okay, now you see, position for the central bright fringe, position of the central bright fringe that will be obtained at O. That means at x is equal to O is x is equal to O, right? That is for n is equal to 0, n is equal to 0, right? Now what will be the condition for dark bright fringe? So let me write that. So first, okay, let me take another slide. Okay, so condition for dark fringe. Okay, dark fringe. So now you see, so that's gonna be x small d by capital D. So it's supposed to be lambda by 2 into twice n plus 1. Okay, so that means positions are something like this: lambda 2, okay, then 3 lambda by 2. Here of course we're gonna get plus minus 3. Okay, right? Hope you have understood this. Plus minus half lambda, okay, and so on, plus minus 5 by 2 lambda. Okay, these are the position of dark fringes. Okay, so here you see x will be equal to twice n. So it can be written this way also. You can take you can multiply the half, then n plus half into lambda capital D by small d. Okay, and this is the position of n plus 1. You can write this way: n plus 1 dark fringe, n plus half lambda capital D by small d. Okay, position of n plus 1 dark fringe, right? Okay, so why n plus 1 dark fringe? Let me explain. Now you see, when you will put 0 for n is equal to 0, then you're gonna have x1, that's gonna be equal to just half lambda capital D by small d. This is the first dark fringe. Okay, first dark fringe, position of first dark fringe. Now if you put n is equal to 1, then what you're gonna have, x2, that's gonna be 3 by 2 lambda d by small d, that's going to be second dark fringe. Okay, right? So when you put 0, then you get first. When you put 1, then you get second. So when you put n, then you must get n plus 1, right? So hope you have understood this. But in case of bright fringe, let me go back to the previous slide. Here you see, when you put n is equal to 0, you get the central bright fringe. That is not the first bright fringe, that is the central bright fringe, and after that you're gonna get the first bright fringe. Okay, when you put n is equal to 1, then you're gonna get first bright fringe. Okay, so hope you have understood this. Now you see, now what will be the fringe width? So how to obtain the fringe width? So now you see, let me take a new slide. Suppose it is a bright fringe, this is a bright fringe. Okay, how to obtain that width of this bright fringe? Now you see, if this is the bright fringe, so here we should have a dark fringe, and below this bright fringe also we should have a dark fringe. Suppose position of this dark fringe is, suppose first dark fringe, suppose this is for n is equal to 1, right? N is equal to 0, that is suppose x is equal to half lambda d by small d. This is the first dark fringe, and this is the suppose second dark fringe. Okay, here second dark fringe will be, if you put x is equal to n is equal to 1, then you're gonna have the second dark fringe, right? So position of dark fringe is given by n plus half lambda capital D by small d. This is the formula, right? So if you put the value of n is equal to 1, you're gonna get the second position of second dark fringe, that is 3 by 2 lambda capital D by small d. Okay, so if you subtract these two, then you will get the width of this fringe, this bright fringe, right? Okay, if you subtract these two, okay, so position means, so here distance from the O, right? So if you subtract these two distances, if you take the difference between these two distances, then you will get the width of this bright fringe, right? Hope you have understood this. So now you see, so just wait. So width of a fringe we can write like this. Okay. Fringe width it can be written this way: beta is equal to xn, okay, minus xn minus 1. So let me take the formula of bright fringe. Xn is equal to, in case of bright fringe, what we have got, xn is equal to n into lambda capital D by small d, right? This was the condition. Okay, right, this was the formula. So you can find it using the formula of dark fringe also. You're gonna get the same result, right? Hope you have understood this. So for x minus 1, it's gonna be n minus 1 lambda d by small d. So if you put this here, x lambda capital D by small d minus n into, not x, this is n into n minus, this is supposed to be n minus 1 into lambda capital D by small d. If you take LCM, or if you take this common, lambda d, capital D by small d common, then n minus plus 1, right? Minus n gone, so we're gonna left with so here we end up getting this lambda d by small d. So this is the fringe width. Okay, so hope you have understood this. So now let's solve few problems, numerical problems based on this topic. So here you see Young's double slit experiment. Monochromatic light of wavelength 600 nanometer is used. Determine the distance of the screen from the slit if the slits are separated by 0.28 mm, and distance of the central bright fringe and the fourth bright fringe is 1.2. okay, distance of the central bright fringe, actually distance between the central bright and fourth bright fringe is this. Okay, so here you see what we're going to do. Here we're going to use this formula, that is position of bright fringe and bright fringe is given by xn is equal to n lambda capital D by small d. We're going to use this. Okay, so here what are the given informations in this problem? Here we have lambda, that is 600 nanometer. Okay, and also slits are separated by 0.28, that means small d is equal to 0.28 mm. okay, and distance between the fourth bright fringe, that means x4 from the central bright fringe is 1.2 centimeter. So x4, we're going to use this formula to find x4. Okay, now let me take a new slide so that I can solve this problem. Okay, so here we are going to find d, capital D. Capital D is the distance between the screen and the slits, right? So this is capital D, this is the screen, and this is these are the plane of slits. Okay, so we need to find that capital D. Okay, so these are the given informations. So nanometer will be converted into meter, 600 into 10 to the power minus 9 meter, and millimeter will be converted to meter, 0.28 into 10 to the power minus 3 meter. Then centimeter also converted into meter, 10 to the power minus 2 meter. Okay, now here you see we know that xn is n into lambda capital D by small d. So therefore here you see x4 will be equal to 4 into lambda capital D by small d. So from here we're gonna get d is equal to x4 small d by 4 lambda. That's what we're gonna have, right? Okay, so now let's put the value. X4 is 1.2 into 10 to the power minus 2, and small d is 0.28 into 10 to the power minus 3 divided by 4 into lambda. Lambda is here this 600 into 10 to the power minus 9. Okay, that's what we have got. So now 4 cancels 1.2, that's gonna be 0.3. okay, then okay, now what we can do, so 0.3 into, okay, let me make it 3 into 10 to into 28, then 10 to the power minus 5, and okay, if you remove the points from before 3 digit, here you should get 10 to the power minus 3. So here we're gonna have 10 to the power minus 8, right? 10 to the power minus 8. Okay, and here we're gonna have 100 into 10 to the power 9, that's gonna be 10 to the power minus 7. Okay, 100 into 10 to the power minus 9, that's gonna be 10 to the power 7. Okay, so 3 cancels 6, that's gonna be 2. So here we have 28. Okay, 2 cancels 28 gives 14, and 14 into 10 to the power minus 8 plus 7, that's gonna be 10 to the power minus 1, and if you multiply these two, then you should get 1.4 meter. So this is the d. So therefore the distance between the distance of the screen from the slits is this. Okay, right? So here is the answer, right? So hope you have understood this question was asked in 2025. This was asked in HS final examination 2025, okay, under Assam Higher Secondary Education Council. So now let's move on to next question. Was asked in 2024 AHS final under Assam Higher Secondary Education Council, right? So now here you see, in Young's double slit experiment, slits are separated by this distance. That means small d is equal to 2.8 into 10 to the power minus 4 meter. Then screen is placed at a distance of 1.4 meter. That means capital D is 1.4 meter. And the distance between the central bright fringe and fourth bright fringe, that means x4, that is given as 1.2 into 10 to the power minus 2 meter. Now we need to find the lambda, that means wavelength. So again we're going to use the same formula, right? We need to find the wavelength. Okay, so again xn is equal to n into lambda capital D by small d. We're going to use the same formula again. So now here we have x to the x4, so here 4 lambda capital D by small d, so which means 4d is here 1.2 into 10 to the power minus 2. 4 lambda is unknown, capital D is 1.4 and small d is 2.8 into 10 to the power minus 4. 2.8 into 10 to the power minus 4, right? So it implies, so let me write here, it implies that lambda is equal to, from this equation we can find lambda is going to be equal to 1.2 into 10 to the power minus 2, then 2.8 into 10 to the power minus 4. So here we can write that 10 to the power minus 6. Okay, just give me a second. Okay, 10 to the power minus 4, 10 to the power minus 2, that's going to be 10 to the power minus 6, right? 10 to the power minus 6. If you multiply this one here, okay, 10 to the power minus 4, 10 to the power minus 2, that's going to be 10 to the power minus 6, right? Hope you have understood this. Divided by this one, 4 into 10 to the power 4 into 1.4, not 10 to the power 1.4. So here you see this 4 cancels 1.2, gives 0.3, and 1.4 cancels 28, gives 2. Okay, so here we have got 0.3 into 2, that's going to be 0.6 into 10 to the power minus 6, right? So we can write this one this way. Okay, just give me a second. 0.6 into 10 to the power 3 and 10 to the power minus 9. Okay, so again if you multiply these two, that's going to be 10 to the power minus 6. Okay, so if you write this result, if you keep the result here, then it's supposed to be meter, unit supposed to be meter, and if you express in terms of 10 to the power minus 9, that's going to be in nanometer. Okay, so here still it is meter. Okay, I will tell you when it will be replaced by nanometer. So if you multiply these two, you're gonna get 600 into 10 to the power minus 9 meter. So here you see 10 to the power minus 9 meter is 1 nanometer, so we can replace it, we can convert it into nanometer. 600 nanometer now. Okay, 600 nanometer. Hope you have understood this. So now let's move on to next question. So this question was asked in HS final exam 2022 under Assam Higher Secondary Education council. Okay, so here what are the informations given? Okay, fringe width in Young's double slit experiment, we need to find the expression for fringe width. So I have already explained earlier how to obtain what is the expression for the fringe width, how to obtain it from Young's double slit experiment. So now let me solve the numerical part only. Wavelength is given here 500 nanometer, lambda is equal to here 500 nanometer. So in meter it's gonna be 500 into 10 to the power minus 9 meter. Okay, then incident on two slits which are 1 millimeter apart, that means small d is equal to 1 mm, that means 1 into 10 to the power minus 3 meter. Okay, then place at a distance of 1 meter, so capital D is 1 meter. Okay, and we need to calculate the fringe width of the fringe pattern, so that means we need to find fringe width, that means beta, and fringe width is given by lambda capital D by small d, as I have already shown you how to derive this. Okay, so lambda is here 500 into 10 to the power minus 9 meter, and capital D is 1 meter divided by small d is 1 into 10 to the power minus 3 meter. Okay, that's how we can do. Now if we calculate this, then what we're gonna have here 500 into 10 to the power minus 9 plus 3, that's gonna be minus 6, right? Then if you multiply 100 from this 500, then 5 into 10 to the power minus 6 plus 2, that's gonna be minus 4. 5 into 10 to the power minus 4 meter. So this is the fringe width. Okay, so hope you have understood this. If you think this is helpful, then please do share with your friends, inspire me to create new contents for you and help me to grow my channel. Thank you for watching. See you in the next video. Bye bye.